Hi, everyone. Welcome back to Tech Talk, a podcast where Amit and I talk about various technology related topics. Today, we're going to talk about electricity grid. It's called different names, maybe in different countries. In UK, we predominantly call it power grid. Power is usually synonymous with electricity in here. So we're going to talk about the national power supply, how it's generated, how it travels through the network, and then into your homes. Obviously, you are watching us in some sort of electronic device, and that device is powered by the electricity that you've either charged your laptop or your phone or your desktop from your home or from work, wherever. And this power is what enables a lot of our day-to-day activities. And it's very important to sort of know about all the technology that goes behind it. And I think in our talks, a lot of the times we marvel on all the little things that makes up a whole system and a user experience and all the things, all the technology that goes behind the user experience. And I think the actual supply of electricity is a very crucial one. I thought this would be a really, really good topic for you guys to know, be aware of, and also be mindful of for the future with the current climate and economic condition. The energy supply is somewhat of a popular topic in the news. So let's talk about it. Amit, what's your thought on this?
I think, first of all, thanks, Rinat, for recommending the topic. It is a very good topic and a very relevant topic. There has been a energy crisis, especially in Europe, with Russia's invasion of Ukraine. What has happened now is that Russia has stopped giving gas through the Nord 1 stream pipeline to Germany, and that has caused a panic. And especially just before winter, because in winter we consume a lot of gas, but gas is just one way to supply the heating, but here we are talking about the electricity. So but what happens if we run out of gas and if you're not able to generate electricity? So I think it is important to understand the different systems that are involved in sending the electricity to your houses, and then figure out, okay, once the electricity is received, what can we do to save it and make sure that we are not consuming a lot of electricity. So in case there is a power cut, we are still able to manage our day-to-day lives. So yeah, it's a very relevant topic, especially in today's world.
Yes, absolutely. And a lot of people are talking about it. I hear in the news every day that the energy supply and a key part of energy supply is electricity. As you said, gas and electricity are the two main forms of energy that we consume as consumers, not just businesses or corporations, but as even at like mass population at homes, we use energy in different ways. And nowadays in UK and potentially in many other countries as well, we're becoming more and more reliant on electricity and replacing our gas stove, gas heating system with electric systems because they are actually a lot more well, it could be controversial, but they are actually a lot more environment friendly than gas. So electricity supply, how it's generated, how it's transmitted, all of these, all of the different areas of electricity from generation to it coming to your home. All of these things are quite important, and it's nice to know about all of these things. So I mean, there are various stages or segments of this, Amit. Would you tell us a little bit more on that, the generation, distribution, etc.?
Well, so whatever I've read and whatever I understand, I think let's break it down. So we receive electricity at our homes and we also receive gas. So here in the UK, for the public who are not aware, in the UK, we, as Rinat mentioned, we receive both electricity and gas to our houses. Gas powers the gas stove, the fireplace, the boiler, and the electricity powers everything else, including the boiler as well, and the gas stove to generate the spark. So now the question is, why do we need two separate forms of energy? Why can't we just use electricity for everything? So UK is actually moving towards that. So currently electricity is much more expensive. Per unit of electricity is more expensive than per unit of gas. So a lot of people in old houses in the UK, they still prefer to use gas because it's much cheaper per unit rate. Of course, you consume then a lot of gas, but if you consume more electricity, then it becomes more expensive. So yeah, so you are receiving electricity in your house. So someone has to generate that electricity. So it is like when the power goes off. So I come from India, Rinat comes from Bangladesh. When we lived there, there used to be power cuts, and whenever there is a power cut, we used to have a backup generator, and that generator used to generate electricity by burning fuel. What fuel? Could be petrol, could be diesel, mostly diesel, and that diesel used to get burnt. It used to move a motor, and that motor used to generate electricity. So that is called a generator. So someone in the UK is actually generating electricity by either burning the fossil fuels like coal, petrol, diesel, or maybe natural gas, etc. Or they're using some renewable sources of energy like wind, solar, tidal, etc. So you have
Mm.
like the non-renewable sources of energy and the renewable sources of energy, and some of these these generators, as you might call them. So I'm just being very like generic because it could be the term could differ from country to country, but in essence, someone has to generate that electricity. So there is a power plant, and that power plant, it could be nuclear as well. So it could be nuclear power plant, coal power plant, hydroelectric power plant. It could be thermal power plant or whatever. Okay, so there are different types of power plants and that generates electricity, and it's there across most of the world. Someone generates electricity, then it comes to your house. How it comes to your house? We see poles and we see cables or wires. So whenever we travel in the highways or the motorways in the UK, as it's called, we see these huge towers of electric poles that are carrying long wires throughout the countryside or throughout your region. So what is that? Why is that? And what is it actually doing? So basically, it is carrying high voltage, low current to the substations. So someone is generating that electricity. That electricity then needs to get transmitted at a high voltage. Why high voltage? Because high voltage means low current, and that means low energy loss through heat. If you have high voltage, you can transmit it over longer distances. And voltage is nothing but the power, how much push are you giving to the electrons in the wire or the
So
electric cables.
this is actually quite interesting. I think we should cover this part of all
Yes.
of these different terms like voltage, ampere, and current, for example, because this is
No, no, no.
actually.
Hang on. Rinat, voltage, the unit is V.
Mhm,
Current, the unit is A, which is ampere. So current and
mhm,
ampere are basically same.
are the
Ampere is the
same
unit
things,
for
yes.
current. And
And
then you have
then we
resistance.
go resistance,
Yes.
and then there is watt hour and watt and
Yes.
all of
But
these
that
things
is
that
power.
we.
That is power.
Yes, yes, absolutely. What is a unit for power in general? I mean, it could even be completely different power, but we calculate power of electricity in watts commonly, right? And this is very interesting because when I finished my A-level equivalent, I was kind of in dilemma whether to study mechanical engineering or electrical engineering. And the reason I chose mechanical, primarily it was because I loved physics and all of those, but also I was kind of scared of all the different terminology of electricity, because I always had this confusion, not confusion, but I always had this, that I always felt like there are too many different things to define electricity. Nowadays I feel like I understand it a little bit more, So I would like to go through it all and have you correct me if I say anything wrong. I feel like that might actually enlighten our audiences a little bit more. The main difference that I always had problem understanding is the amperage and the voltage, and the difference between the two. And the way I finally understood it when I compared it to water pressure. So if you have a water, a big tub of water, and if you have a hole where a stream of water is coming out, the speed at which the water is coming out, that's like equivalent to voltage, the speed of transmission. And the amount of water that is actually held in the tub, that's the actual, the actual substance or actual amount of energy, if you call it in electricity terms, that's the ampere. So you could also compare it with heat as well. So say, for example, the actual heat energy that is stored somewhere, that is the heat energy that is expressed with kilojoules or joules. And then the temperature, what we measure, is actually not the actual heat energy, but when it's being transferred, or correct me if I'm wrong. So that temperature could be synonymous with electricity voltage, and the kilojoules or the joules, the actual measurement of how much heat energy is stored somewhere, that's like ampere, which is actually the actual representation of how much electric energy is stored in a battery or wherever. And the transmission speed is the voltage. And this was very confusing when I was in A levels, and hopefully I've explained it well, so it helps our audience to understand it a little bit better.
Definitely. Actually, it helped me also understand it much easier. So I think, yeah, it definitely helps. And if you look at the equivalent in a wire, so as you mentioned, voltage is the speed at which it's coming out, and ampere or current is basically the energy that is there in the actual thing.
Mhm.
So let's say that you have a very long cable and you want to transmit electricity through it. So you put a lot of energy, so that's the speed. So it's coming with a high speed, but low energy. Low energy means low wastage. Low wastage through heat because the wire gets hot, so you lose the energy through heat. So now if it has high energy, it will lose a lot of heat. But high energy, short distance, fine. Then so you have high energy but with low voltage. So high current with low voltage. So you don't need to give that much push. So speed can reduce, and then you have high current. But if you have to send it over a long distance, you have high voltage, low current. So that's the basic essence of the transmission. So someone has generated the electricity through some means, and then there are these transmission wires and these huge things. Now there is a another step in between. So basically, when the power is generated from the power station or the power plant, what happens is it is stepped up. So there is a step up transformer and a step down transformer. In order to facilitate transmission over thousands of kilometers with very less energy loss, the voltage is increased considerably, almost up to 4,000, 400,000 volts in the UK, or 400 kilovolts. So that's 400,000 volts. And that is then transmitted to, say, thousands of kilometers away, and then it is stepped down. So now the voltage is reduced. Once the voltage is reduced, say from 400,000 to say 300,000 or 200,000, then it's sent to a small substation. And that substation then transmits it to various locations or various entities. These could be industrial. Industrial is anything that does manufacturing, anything that does producing. So what do you mean by that? Say a factory. A factory is industrial. Okay, then they require a lot of energy. A steel plant, that requires a lot of energy. So those are some of the things which are industrial in nature. Then you have commercial. Commercial is something like a grocery store or a shopping mall. So those are commercial spaces. And then residential. So those are all the places where people actually live. So those are the three main types of these are basically the three different types of consumers. So you have the electricity that is generated, then it is transmitted, and the substation distributes. So normally a substation is close to where you live. So that the transmission can happen over long distances, but the substation then transmits it at the voltage that you need. In the UK, the voltage that we receive at the socket is about 220 to 230 volts. So that's the voltage that we receive in the plug, in the socket. Uh,
So I
Go ahead.
have a bit of a confusion or a question to understand in here. So I know that there is like a certain in certain situation, it's not actually dangerous for humans to touch. I mean, in no way am I suggesting our audience to ever try this, but I want to understand, like, is it the amount of volt that becomes more and more dangerous, or is it the amount of ampere, or is it what makes? Because I've known, I've seen videos, or like there are people who jokingly, or for fun, touches like an electricity supply, but wearing like like plastic shoes or sandals, so they don't touch the ground, and then they form a line of people, but nothing actually happens because so what is that phenomenon? How does that work?
So basically, this is a concept of path of least resistance. Electricity always tries to follow the path of least resistance. So that's why you have, I mean, it's not related to the topic that we are discussing, but it's
Okay.
good to know that you have something called as a earthing wire in your house. So when lightning strikes, the lightning then goes to the earthing wire, and that takes the electricity from the side of your house, from the top of your house, to through the side all the way to the earth, right? So that's the path of least resistance to earth. It can go in multiple directions, but that's the path of least resistance. Otherwise, if you don't have that wire, what will happen is it will actually hit your roof or some other device in your house, and it will take that route. Okay, so that's why a lot of times people wear something so that the electricity doesn't go through their body but goes through outside their body through some kind of a glove or etc. And they ensure that it doesn't they are not connected to earth, because what happens is your body then becomes a conductor. So your body then becomes the path of least resistance, and because you have maintained a connection between earth and the electric supply unit, then the electricity just flows through your body and you get a shock. So that's why it's very important that you don't touch high electricity cables. I have actually got electric shocks by while touching the power socket unit inside a computer. I literally, because it was AC current, I had a chance to remove my finger, but the effect was this. When I touched the power socket unit, the plug, where the right behind the plug, there are these cables and there are screws. I touched my finger there and I connected the power cable. I didn't realize the switch was on. So my fingers got stuck. So it's like electric shock. And because I'm now the path of least resistance, electricity is flowing through my body. It was in my left hand. So when I touched the power socket, I mean the screws and the wires at the back of the socket, the electricity started flowing. Now what happened is my thumb got stuck, so I could not remove it. So I had to put a leg and then push and like literally pull my finger away. It required a lot of effort. My skin from my thumb got peeled. I had a very slight bleeding because it was not a very deep cut. It was a very small cut. And the good thing is it's alternating current. So in alternating current, the supply goes on, off, on, off, on, off. So you can actually get rid of your finger or get rid of the device if it is low current. Of course, it was very low current, so I was able to. I didn't receive any major, I mean, like injuries, except that where my skin got peeled
but
off
but
and then the
but
blood came.
but it was left hand, you said, but isn't it directly connected to your heart? Isn't it? A lot more dangerous
So,
because
so
that,
I'll tell you what happened. So basically what happens is the moment the electricity starts flowing through your body, all the water starts evaporating
oh,
or they start getting boiled. So basically I had burning sensation on the left side of my body, even though nothing was burnt.
wow,
But
that is a
but
phenomenal
that is but
experience.
that is a start, right? When you see movies, you see when people touch something very high power, high electricity, voltage or whatever, they get electrocuted, which is basically they turn into ashes or they burnt, they
Mm,
get fire. Basically, it's that. It's heating up your body to a very high temperature and then you catch flames.
wow, that is
So it is very
definitely
dangerous. So
very
I was
dangerous.
very lucky. I screamed, I shouted, I was in my senses. I was very young. I was in school. I can't remember which year it was, but yeah. So when that happened, I realized that whole half of my body, from the tip of my finger all the way down to the tip of my toe, I could feel that burning sensation. It was very weird because I could feel it only one part of the body, not the other part. As I said, least resistance. So the electric current doesn't have to go from my left hand to my right leg. It can go from my left hand to my left leg because it's the least resistance path. But anyway, that's not the focus of this topic.
No, this is, I mean, electricity, transmission is actually, quite relevant to this, and this is actually really, I suppose this is important as well because I never had such experience. I mean, I had various electric shocks dealing with PC hardware and all of this, and a lot of the times I ignore it because I thought, nothing actually happened or it's very mild. And I used to have this laptop, which was like a metallic outer shell, and every time I would touch it I would get a mild shock, but I thought it's just not. But now from this I am going to be a lot more careful because these all of these things are very easy to happen around your home, and you have electric outlets everywhere. So this is actually quite eye-opening, and hopefully this is eye-opening to our audience as well, how dangerous it can be very quickly in a split second. So I'm going to be careful, and I very much strongly urge everyone that's listening to also take this story as a like an eye-opener, and change your habits and turn off anything electrical before you do anything. And I guess always wear gloves and sort of non-conducting shoes when you're having to deal with anything electric.
I think, yeah, that's a very good advice. Always wear a non-conductor in your hands and in your legs, so that if in case you touch something that is having current going through it, then you don't pass that current to earth. So that's how you protect yourself. Anyway,
Now,
yeah, go ahead.
sorry, just like one other thing that I just thought of, and this I also is quite interesting. And with all the recent Nobel Prize, with all that quantum entanglement and everything, this just makes me think that how does I mean, if a current is flowing, right, and then the path has been divided into two options, how does it know which path is the path of least resistance without actually going through both paths before? And it just came to me as a question.
The path of least resistance comes from the resistance of the material itself. It'll try to
Oh
go through
no, so
both
it's
paths.
not necessarily the longer path.
No,
It could, okay. So
path
it
of
could,
least resistance. So least resistance,
so it's a technical, the resistors and the resistance, the electric
exactly.
technical
Yeah,
term.
yeah, yeah.
Right. So it could be a copper wire, which is usually a
Very
least
good conductor.
path,
Yeah.
very good conductor, but a very long copper wire to earth. But it could be a non-copper, or not very good conductor on the other option. It will still go to the copper wire because it doesn't
It's
know
easy
how
to
long
go
the
through
path.
it. It's easy to go through it, right? So if you have a small hole
Right.
or a big hole, the water will flow through the big hole, right? It's
Yes,
path of
yes.
least resistance. So it's that
Right,
simple.
okay. That's actually a very, very good anecdote to understand as well. Because yeah, I always thought that I always hear this and I keep thinking it's the length of the path, but no, it's not the length. It's the conductivity of the
The
material
material, exactly.
inside.
So that's why
Right.
least resistance. That's why the stress is on the word least resistance. It is not
Mm-hmm.
on the shortest path. That's why it's path of least resistance.
Ah,
Anyhow,
that's
so
interesting to know.
So we've got we someone has generated the electricity. It has been then transmitted. The transmission has happened. Then it comes to a substation from where it gets distributed to industry, commercial spaces, and residential. And that's basically the four different parts: generator, transmitter, distributor, consumer. In between, you will have a supplier. So the distributor could be different from the supplier. Supplier is with whom you buy the electricity. They manage the bill, they manage the consumption, they fix the unit rates, etc. So that's basically the grid. So someone generates power, someone then transmits, and whoever is generating the power, they are different from the one who's maintaining the network. The network has to be maintained. So the network, what do you mean by network maintenance? So someone has to service the poles on which the wires are hanging or the towers. They have to service the cables. If the cables get cut during a storm or a thunderstorm or like a cyclone or anything, then they have to be repaired. So someone needs to go up and fix things. If a bird is accidentally stuck in that cable, it's causing a loss of energy, then that has to be removed, etc., etc. But you have to understand that uh, why the grid is so important. So we call it the power grid or the electricity grid. In the UK, you call it the national grid. So it's different terms all across the world, but in essence, it's a power grid. It takes power from some place and then transmits it via grid. Grid is nothing like but a network of different towers and wires that are spanning the country that takes the electricity. Now, this is a wired way. It is like you are having a wired internet, like we spoke about in our last topic, Wi-Fi. And then you have wireless internet. So there you don't need any cable. So then you have wireless. Can we have wireless electricity? So yes, that is possible, and that is something called wireless chargers. So you don't have to actually physically connect a wire to get the electricity to your smartphone. But what you do is you just place the device on the wireless charger and it transmits wirelessly without a wire to the device. But that happens through a magnetic coil. So in electricity, electricity is actually synonymous with magnetism. So if you have electricity, then it's a magnet. And if you have a magnet that you keep rotating, you can generate electricity. So that's why they are all interconnected. So
Yeah, electricity and magnetic is very much interconnected. That's why we have electromagnetic fields, right? So it's
exactly. So
one.
you can, if you don't have a natural magnet, you can create an electromagnet. An electromagnet is nothing but a metal wrapped with a coil of wire, say a copper wire, and that copper wire is carrying electricity. And because that electricity is being carried across that metal, it generates a magnetic field, and that becomes an electromagnet. And with a natural magnet is something that exists in nature. You take a piece of iron or something else, and that becomes a magnet, and that can attract without any electricity. But if you move that magnet across a piece of coil or a copper cable, if you move that natural magnet inside the coil up and down, it will generate electricity in that coil. So it works both ways.
Yeah, magnet, I always found it to be so interesting. And magnet is one thing that is like magical to me. I mean, it's just,
It is
in
magical.
our physical world, we kind of know how everything works, but this is one thing that is like, there is no physical anything to push or move anything, but it is still moving. And it was really fascinating to me when I read it when I was in school on how it works and how each of these the poles of atoms are sort of aligned to create the magnetic force. It was very interesting, and it was amazing to find out the fact that it's not like a some sort of deity that's making it happen, but the atomic structure of a metal that's behind it.
Yes, and the thing is that each magnet has a north pole and a south pole. So basically, it's a dipole. So there are two poles in a magnet. be it an electromagnet or a natural magnet. So scientists are now trying to see if there are monopoles, a magnet with
Mhm.
just one pole. Unfortunately, till date, we haven't discovered a monopole. Whenever we have looked for a magnet, it exists in, and no matter how small it is always with two poles. So we have only observed dipoles in nature, not monopoles. So
Right.
that's a interesting fact, but it has got nothing to do with the electricity grid.
All right, let's come back to our electricity
Yes.
grid topic. So you've mentioned generation of electricity and then transmission and then distribution also to the sub networks. And then is there any other like
So
sector?
I mentioned suppliers from whom you
Hmm.
buy electricity.
Hmm.
So the distribution could be to these residential, commercial, and industrial places with the help of the suppliers. So the suppliers are in essence from where you buy the energy and to whom you pay the bills, and that's your supplier. And they provide you with a meter, and they take your bill. They change the unit rates based on the demand and supply, etc. Uh, based on peak hours or off peak hours, etc. So yeah, so based on all these things, you have your bill, and that bill keeps changing based on how much you consume. Now there are a couple of things that we need to keep in mind. So electricity is generated and then someone is consuming it. So there is a demand and there is a supply. The demand and supply has to always balance, and that balancing is called the balancing of the grid. Now what does that mean? Suppose there is a lot of demand. So there is a lot many people are consuming electricity, but the supply is not enough. So you have an electric current, an alternating current going through your wire, and that wire is carrying the electric current at a particular frequency. That frequency in UK is 50 hertz, and that frequency varies from country to country. Each grid has its own frequency that they have to manage. Now, why is this frequency important? If you know about alternating current, an alternating current goes like a sine wave. It goes up and down across the horizontal axis or a vertical axis or any axis, it goes up and down. So when it goes up and down, over say during say it goes 10 times up and 10 times down, that's 10 hertz. So that's basically the frequency. In 1 second, how many times it goes up and down? Okay, if it goes up and down say 50 times, so that's 50 hertz. So that's the unit of, and that's called frequency. How many ups and downs in 1 second? That's basically the frequency. Now you would ask, why is it important? So let's say you have a lot of demand, but there is not enough supply. So the frequency drops. It gets stretched. A lot of people are trying to consume the electricity, but the generators are not able to provide enough electricity. So then you get power cuts because you have to balance the grid. Now you say, why do I have to balance the grid? Well, if you don't balance the grid, your electric devices will stop malfunctioning. Your electronic devices will stop malfunctioning. Now, what does that mean? Each electronic device or electric device, they are meant to what do you say? They are meant to run at a particular voltage and at a particular frequency. Now, if they don't receive that same frequency, they will get damage or they will not work properly or not work effectively. So it means if the grid is balanced, then you need a power cut. If there is a lot of demand but less supply. What happens if the reverse is the case? In the reverse option, what happens is the demand is low but the supply is high. Now, if the supply is high and the demand is low, the frequency increases. Now, that is also not good for the devices because they'll not operate effectively. So, the frequency has to be dropped.
So is it like, if I imagine in my head the waves going up and down, and if there is nowhere for it to go, if there is this hard stop at the end, then the frequency keeps coming and they get squashed together, which is basically the higher frequency because and if there is going, being consumed too much, but there isn't enough coming
Exactly.
from,
Yeah.
then it gets elongated, so the frequency reduces. Is that how?
Reduces.
Okay,
It
that's
is
very
at a
interesting.
high level, that is what it is. We don't have to
Okay.
go in depth, but it is important to know that there is a frequency of electricity that you receive from your electric supplier, and that frequency is standard for a country. So we talked about the balancing of the grid, and that's what balancing means. You balance
Mhm.
the demand and supply. So if you have more supply, what happens? You export. If you have more demand, you import. What do you import and export? You import energy from other countries. So UK imports energy when there is a huge demand in the network, and it exports energy when there is the huge supply in the network. So you offset, and that is what the power grid or whoever maintains the transmission network, they have to constantly keep monitoring. The frequency has to be within I think 0.5%, within say 5 hertz, 5 hertz, 2 hertz to 5 hertz. So it has to be in that range. If it is more or less than that, then it's a problem. Sorry, not 2 hertz, zero point 0.2 hertz, zero point 0.2 to zero point 0.5 hertz, and that's the balancing of the grid. So that is very important, that the grid is always balanced, otherwise your devices will stop functioning. So you have the electricity coming to your house at a particular frequency, and at a particular voltage. So that voltage also has to be maintained. Every socket in the house will have a particular voltage. Now, think of it like this. You have connected one, say, an extender, okay, an extension cord. So that extension cord basically takes, you connect it somewhere, and it has say 4 plugs. Now, each plug, okay, each plug is drawing some current, and that current is then powering the device. Some devices draw more current, some devices draw less current, okay. If the device draw more current, it has more voltage. If it draws less current, it has less voltage. And that is basically the difference between a smartphone and a desktop computer or a laptop, or maybe a light or a monitor. Each device that is there in your house is drawing different current, and that current is coming from the socket. Now the socket is rated for a particular amount of current. If it exceeds the current, then your device can get short circuit. It can get burnt because it is receiving more current than it is needed. So there is a fuse on
Mhm.
the socket. I mean, this is a new safety thing. Earlier, there never used to be such things. But if you draw more current than what is actually rated, then you can actually either burn the socket or you can burn the device because you're consuming more current. So each socket is rated, say, 10 ampere. 10 ampere is a lot of current. 1 ampere, it will give you a huge electric shock. Most of the devices are rated at milliamp hour. So like in 1 hour, how much current are you drawing to run yourself? So basically
Mhm.
to run the device. So that basically that is, it is very important to understand that because I had an electrician in my house, and I asked, why is that rated at this current, and what happens if I connect like 10 devices to one socket? He said it's fine because they are not drawing a lot of current. I said, oh, that is very interesting.
Mhm.
So this is something important to know. Like to one socket, I've actually connected 10, I'm physically connected 10 different devices. They are physically drawing power either through my monitor, through my
Mhm.
extension cable. There is a printer, there are
Yes,
two
absolutely. I
monitors.
mean, especially all the computer-related devices, those are electronic devices. They draw very little power, but they do a lot, in our lives, a lot of work. But actual current drawn, the actual energy, the consumption is relatively low. So yeah, I've done exactly the same. From one socket, I've connected so many, and you get extension leads, and then extension leads connected to another extension leads. But if you sort of connect something like with a really high power draw, like for example an iron or a electric heater, then it might be dangerous. But a few of
Yes,
them.
it might be dangerous. It can cause a short circuit. It can cause a trip. It can cause many things. So yes, you have to be very careful about it. And that is why the grid has to maintain that voltage, but that voltage has got nothing to do with the electricity that's coming in. So yeah,
Mm.
so it's all, so you can actually draw more electricity with that much speed.
Mm, yeah. So okay, so we kind of covered the whole of the cycle from generation to transmission to distribution. And was there any other segments of the journey?
Supplier and then the
Hmm.
consumer. So those are basically the different elements in the grid. And it is i- see, we have covered from a UK perspective, but it applies to any country. You have to generate electricity, you have to transmit it, someone then distributes it to industry, to commercial spaces, to residential houses, and then and these houses they actually buy their electricity from a supplier and they pay their bills to the supplier. So that's the whole grid. That grid has to be balanced. So we talked about supply and demand, and the grid has to transmit electricity at high voltage, then it steps down to a low voltage so that the energy can be conserved and we don't waste a lot of energy in terms of heat. So yeah, these are in essence, this is the whole idea behind an electricity grid or a power grid or a national grid, whatever you want to call it.
Right. Okay. That was very knowledgeable. To be honest, I've learned a lot. Thank you, Amit, and hopefully our audience did too. And this was a very enjoyable topic to cover. And yeah, audience, if you guys have anything to add, or if you guys think of a topic that we should cover, or if you guys would be interested in joining us as a guest, please do reach out. Our contact details are, in every platform that you can hear us or see us. So yeah, please do reach out with any feedback or any communication. We look forward to seeing you in our next episode. But yeah, hopefully you guys stay safe with all the electric outlets around you, and hopefully I will see you guys next week.
Absolutely. Thank you so much, Srinath. Bye.
Thanks.